Yeah, so I will be talking about locality-sensitive orderings. So in general, in theoretical computer science, and I guess in math in general, we like big hammers, or we like tools that make hard problems into simple ones. And some examples being maybe dimension reduction, like in the metric case, or WSPDs, metric embeddings, and such. And in this context, I introduced to you locality-sensitive orderings, which actually will be introduced by Chan and Har-Peled about 4 years ago. So locality-sensitive ordering is a tool that generally make a metric problem, reduce it into the line metric in a sense. So let me dive into the definition. So you're given some metric space X, and the locality-sensitive ordering, LSO, is a collection sigma of orderings. There are two parameters, tau and rho. So you have tau ordering, so this is just orders over the points. There's no distances or anything, just first point, second point, and so on, tau times. And the guarantee is that for every 2 points, you have one of these orderings. For every 2 points, there are one of the orderings when these points are almost consecutive. So what do I mean by this? So you have all the points between x and y should fall in the ball of radius rho times the distance between x and y around x or y. And so in this sense, they're almost consecutive. Everything which is between is very close to one of them. And you should think here of rho as being a very small parameter, like 1 over 100 or something like that. And so Chan, Har-Peled, and Jones showed that for d-dimensional Euclidean space, you always can construct this locality-sensitive ordering such that the number of orderings is exponential in the dimension. So epsilon to the minus d. And this is true for the entire space. There's nothing discrete here. So let me maybe tell you, so one application of why these orderings are useful. So consider the nearest neighbor search. So if I'm just, so in this problem I have n points, and I need to construct some data structure, so that given a query point, I can quickly find the nearest neighbor or approximate nearest neighbor. So here's a very simple solution using these LSOs. So I just store all these points sorted according to the orderings, and now given, say, a query x, I will just check all my neighbors to the left and to the right. And among these 2 tau neighbors, I'll just check them one by one, and the closest one will be my answer. So this is a good answer because if y is the closest neighbor, so when I will check the ordering that satisfies x and y, the neighbor to the right will be very close to y, and therefore this will be a 1 plus epsilon approximate nearest neighbor. So this is a super simple solution. And in general, using these LSOs, the applications are usually quite straightforward. Yeah.
If you have x and y, all the points that are close to x and y belong
No.
the other way.
The other way around. All the points between x and y should be close to either x or y.
Okay, so but then how was that a good solution then? Because maybe the closest point to y does not appear between the points.
This is a good solution between, you guarantee that all the points in between are very close to x or to y. Now y is the nearest neighbor, and therefore all the points here should be very close to y. So by triangular inequality, the distance between x and z will be like 1 plus epsilon approximation. So Chan et al. Showed many applications for example, dynamic nearest neighbor search and closed pair and the like. And let me maybe tell you how they constructed this. This is not very complicated. So this is using the quad trees, which is a very useful approach in computational geometry. So you take your grid here. Let's talk about the plane. You partition it into 4 points. And now you have this kind of say all the points in this quarter will come before these points, which will come before these points, which will come before these points. So this thing called the Z space filling curve. And now you will recurse on each such quarter. So you will partition these 4 points, and now you have the order over all the points. And inside each part, you will again repeat this, and again and again. So now this is one ordering. And if you shift it enough times, it will satisfy every pair of points. And if instead of partitioning into 4 parts, you'll partition it to 1 over epsilon square, you'll get your epsilon guarantee. While the amount of orderings you need is like epsilon to the d times the polynomial number of shifts. Okay, so this is the story about Euclidean space. Now next I would like to talk about doubling metrics. So doubling metrics is some generalization of the notion of dimension, in particular for Euclidean space. So every d-dimensional Euclidean space has about d doubling dimension. And the definition of doubling dimension is that every ball, we say that a space has doubling dimension d, if every ball of radius r can be covered by at most 2 to the d balls of half the radius. So, for example, this ball can be covered by 7 balls, and therefore the doubling dimension of the Euclidean plane is log 7, or 3. So this is a very useful notion, and in many cases, algorithms that work for Euclidean space will work as well for doubling metrics, using this much more abstract approach. And the one thing to know about doubling metrics is that the number of points you can pack in a ball of radius r, where all the points are a distance about delta, is bounded by r over delta in the power of the doubling dimension. So Chanet already were interested in LSOs for doubling metrics, and they constructed LSOs where the number of orderings were epsilon times log n in the power of d. So this is kind of unsatisfactory because this log n factor, so log n to the d is quite big. And together with Lee, we kind of removed it and improved the result to be equivalent to the Euclidean case. And let me tell you about a bit how we constructed this type of LSOs, and afterwards I'll show you some applications. So the first thing to know about this is this notion of ultrametric, or HST, hierarchically well-separated trees, which is a very structured type of a tree. So one way to define it is using the strong triangle inequality when you use max instead of plus, but here is alternative definition that will be useful for us. So an HST is like a map. We say that a metric space is an HST if you can map the metric points into the leaves of this rooted tree, such that each node in the rooted tree has some label, and these labels are monotone. That is, the label of each leaf is 0, the label Li is smaller than Ld, which is smaller than Lb, and so on. And the distance between every 2 points, which are 2 leaves in this tree, are simply the label of their least common ancestor, the LCA. Yeah, so the distance between V5 and V6 will be the label Lb. Okay, so you can implement this as a shortest path metric on a tree, but generally this is much more structured and very useful. And many of the metric embeddings you know, like FRT, are into this type of creatures, HSTs. So we actually be using an even more structured thing, which we call KHST, where the only difference is that we guaranteed that the difference between any 2 consecutive labels will be at least a k times. So LD should be k times larger than Li, and LB should be k times larger than LD, and so on. So each time you go up, you jump by at least k factor. Yeah?
Sorry. So gamma here, what is the relationship between gamma and the labels?
Gamma is just the label. So this is gamma is kind of the distance between x and y is the label of their LSA. So gamma is kind of the label of D, or yeah, just notation. So yeah, so here's a claim. For every KHST, you can construct of maximal degree delta, you can construct delta over 2, 1 over k LSO. That is mean you can construct delta over 2 orderings such that for every 2 points, all the points between them will be like a k fraction of the distance in the ball of this, yeah. So the construction is quite simple and recursive. So yeah, consider your HST, and this is the root with label LR, and it has at most delta children with labels LA, LB, and so on. So the first step, by induction, we construct these half delta LSOs for each one of the children. So this is the LSOs. And now we construct delta over 2 orders over these nodes here, internal nodes. And the only guarantee is that for every 2 internal nodes, there will be some ordering where they are consecutive. And one way to think about it is that given like a clique graph, you can cover all the edges in the clique using half delta Hamilton paths. So You can convince yourself that you can do it using delta square, maybe it's quite easy, but actually the right answer is half delta. Yeah, so in a sense, what we did here is just we constructed delta over 2 kind of Hamilton paths of these nodes. And now we replace each node by some of the ordering that we constructed. Yeah, so in the first ordering, we put like the first ordering of each internal node, in the second one, and so on. And that's it. This is the construction. So it's not really important that we put the first together, but what is important is that each ordering here is implemented somewhere. Right, and now let's say that every 2 points, x and y, are indeed satisfied. So if x and y fall in the same node here, have the same fuzzer, then by induction, they were satisfied somewhere in the orderings one of this, and it was implemented somewhere, so it's good. And from the other hand, if they come into different nodes, then then for every z between them, it should be either a children of like LB or F, and therefore the distance between x and z will be this label, which is k times smaller than the distance than the label of the R, and this label is exactly the distance between x and y, so we get the guarantee. Okay, so that's that. This is how we construct LSOs for HSTs. And now to get from HSTs to doubling metrics, use a HST cover, which is similar to the 3 covers that were discussed by Hang, I guess. No, but by Chung? Yeah, okay. Yeah, I missed the talk, unfortunately. However, so an HST cover is just a collection of HSTs such that every pair of nodes is satisfied by one of them. That means that you have 4 parameters here. So tau is the number of HSTs, and you have this k, so you want them all to be k HSTs of maximum degree delta. And the guarantee that for every pair of points x and y, there will be some HSTs such that the distance in this HST is like at most rho times larger than the original metric distance. And the theorem that we proved that for every space with doubling dimension d, you can construct this type of HST when the number of orderings, number of trees is epsilon to the minus d. The guarantee here of the distance is 1 plus epsilon. The maximum degree is the k here is 1 over epsilon, and the maximum degree is epsilon to the d. And now given these HSTs, you just construct the LSO for each one of them, and using this claim that we proved, and all of them together give you this collection of LSOs. Because for every pair of points, they've been satisfied by some HST, and in the LSO that you will construct for this HST, the distance between them will be satisfied. Okay, so I guess the magic happens here, but yeah, unfortunately, because of time, I will skip this somewhat technical proof and move to discuss some other aspects of this definition of the LSO. So yeah, we saw this definition of LSO, which were great for Euclidean metrics and for doubling metrics. However, if we consider some other metric spaces, for example, general metric spaces or even like trees, then it seems quite useless. I mean, this row is supposed to be small, but even for a star, you already cannot do anything. So yeah, so we came up with some generalization of this definition of LSO to other metric spaces. And the first generalization is to triangle LSOs. Yeah, so this kind of have a very similar definition. So you again have this collection of orderings. And the guarantee here is that, again, you have tau orderings. And the guarantee is that for every pair of points x and y, there will be some ordering such that like all the points you want to count between x and y, so previously they fall into a ball of small radius around x and y. But in general metric space, this is something that you cannot achieve. What you can achieve is the following. So for every pair of points u and v, which are between x and y, the distance between them will be at most rho times larger than the distance between x and y. Okay, so and typically here, this parameter rho should be large, or larger than 1 at least. I mean, with 1 you cannot achieve much, but with like, yeah. And we get some results. For example, for general metric space, you get this usual trade-off of k and n to the 1 over k. And yeah, so you can get n to the 1 over k orderings, so that for every pair of points, like all the points between them will be a distance at most like 2 to the k times the distance between x and y. And some other examples being, for example, high-dimensional Euclidean space. Yeah, so for this case, if you have like dimension log n, then this type of orderings is not satisfactory because, I mean, the number will be about n. So, I mean, given n orderings, I can do everything in every metric space with like rho being equal 0. But I want the number of orderings to be small. Yeah, so here you can see that, I mean, once, for example, you plug in your distortion to be square root d, the number of orderings will be d, which is like now useful. Yes?
Sorry, how is this definition different from just like requiring that all the points between are contained in like a row dxy ball around?
So it's different a bit. If you take the previous definition, you will lose here a factor of 2, because this is the main work. It will be a 4k.
Okay.
But other than that, it's quite similar.
Okay.
Yeah. Yeah.
For the classical, so epsilon is close to 1? Or
Yeah, here epsilon should be like less than half even.
okay.
Other questions?
So maybe I missed in the beginning to take the space filling curve, like I'm talking about Euclidean space and it's randomly shifted somehow. Is that going to be a Locality-Sensitive ordering?
So a single curve.
A space filling curve.
So, I mean, when you look about these orderings, each one of them is a space filling curve in a sense, but you need to take several to cover all the points.
Right, and the randomly shifted somehow.
So, I mean, it's not really randomly because it's something that well defined for the entire space. So, I mean, you can construct them randomly, but once you constructed them, they are there. And actually, randomness is not really required here.
Okay, we'll talk to you.
Yeah. In this construction, you actually do use randomness because, I mean, we don't have this nice vector structure, but once you constructed them, they exist and you use them. It's not like you need to compute them for each application from scratch. Yeah, and they also have some of these applications for high-dimensional Euclidean space. And yeah, and finally, we get, I guess, to the thing that I guess will be of most interest to the most people in this room. So, for example, planar graph or trees. So, yeah, this both definition, you can apply them, but they will not be better than general graphs. So you don't really use in any way the topological structure of these graph families. And for this, I mean, we were thinking how to apply it, and we get up with this kind of, I guess, quite weird definition of left-sided LSO. So yeah, so I'll define it, and then I will just construct one of them to get you the feeling. So a left-sided LSO is similarly like a collection of orderings, but now the guarantee is that each point appear in at most tau orderings. So the total number of orderings might be very large, for example, even linear. But each point x is supposed to appear in at most tau of them. And the guarantee is that for every 2 points, x and y, they must appear together in some ordering, and this special ordering, so they will not be necessarily consecutive. The property that they will have is that for every 2 points, x prime and y prime, the distance between x prime and y prime will be at most rho times the distance between x and y. So yeah, this is quite strange. It's unclear from first glance why this thing will be even useful. But yeah, but I will show it quite useful. And yeah, and I guess the best way to digest this definition is by constructing this left-sided LSO for trees. So yeah, so let's just do that. So the theorem is that every tree metric admits a log n 1 left-sided LSO. This means that you have log n order, so that each vertex appears in most log n of the orderings, and the row here is equals 1. So for every 2 points, x prime and y prime, when x is x prime before x in the ordering, and y prime is before y, the distance between them is at most the distance between x and y. And this is the construction. So consider your tree and take the separator. So the separator of a tree is a vertex that if you will remove this vertex, the tree will be a partition, each connected component will be of size at most half n. And now the first ordering will simply order all the points with respect to distances from the separator. So the separator will be first, and then V2 will be the second, the closest vertex to the separator, V3 the second closest, and so on, when V14 is the farthest vertex from the separator, where it is here, this one. Okay, and now you remove the separator, and you recurse on each one of these connected components. That means you find a separator in each one of them, and you order all the points with respect to the separator. Now, no, this is 3 different orderings. So here I order all the points in this connected component with respect to this vertex, and so on. And now I remove the separator, remove all the singletons, and continue. So this is it. So it's quite clear that, I mean, after log n steps of this process, I will delete all vertices, and therefore each vertex belongs to at most log n different orderings. Now let's see the second property. So consider a pair of points x and y. I should argue that in some ordering, like all the points that come before x and y are closer than x and y. Yeah, so the ordering that we consider is the ordering where x and y fall into different connected components, or the first time, actually the only time, when we choose a separator on the unique path between x and y. Now, so this is this ordering, and all the points are ordered with respect to distances from the separator. Now, for every x prime and y prime that come before x and y, the distance between x prime and the separator is smaller than the distance between x and the separator, because x prime comes before x in this order. And the same holds for y prime. And therefore, the distance between x prime and y prime going through the separator, they maybe even don't have to do that, but if they do it, will be smaller than the path going from x and y, which must go through the separator by definition. So we get this property with rho equals 1. Okay, so this was the construction for trees, and we get, I guess, somewhat similar constructions for planar graphs, minor free, tree width, and so on, when the number of orderings is linear in 1 over epsilon, and we have this log square n here.
This is the number of orderings, or the number of times that the vertex belongs to somewhere.
The number of times the vertex belongs to an ordering. So in this construction, you can see the number of orderings probably will be linear. Yeah. But but usually what's important is the number of appearances, I mean, for applications at least. Yeah.
So for this construction of the ordering, in this case, really, like the ordering, you could think of it as like being shaped. Like you have one ordering like on the bottom, one ordering on the top, and then x on one, y is on the other, right? And then you have the so like.
So you can think that you put like a shortest path, and then you flatten it on a like a single dimension, and this is the order.
Yeah, then like you flatten it on a single dimension. So, I guess you're right.
Yeah.
I guess like the question is like do your other constructions of these orderings kind of look similar to that, or?
So when you talk about left-sided, this is usually the thing. I mean, with planar graph, for example, the construction is kind of to take a separator and then collapse everything to the separator in like 1 over log in different ways, so that you'll satisfy everybody. More or less, yeah. Other questions? Yeah.
Log and tight.
For trees, I would believe so, but yeah, we didn't prove that.
But you don't know, like if you had stretch, even 1 plus epsilon for trees, for all you know, you get
If you,
constant or something.
what you mean for planar graphs or for trees?
Oh, for trees. I allow myself a little bit of stretch on trees.
I mean, you cannot get less than 1 under this definition.
Or like more, if I allow myself more stretch.
Then maybe you can get larger.
Okay. You don't know any look at that.
Yeah, I don't know other trade-offs. I would believe not, but yeah, I don't know. Okay, so let's move to some applications. to convince you that these creatures are indeed useful. So the first one is to spanners. So spanners were discussed in this workshop several times. But the spanners I will talk about are geometric spanners. Well, it's a metric thing, so there's no subgraphs involved. So this is the definition. You're given some metric space X. And a metric spanner is a subgraph, or it's just a graph over these points, such that the weight of each edge is the metric distance. And so this is a spanner. And we said it's a t-spanner or a spanner with stretch t if for every pair of points, x and y, the shortest path distance in this spanner is at most t times the metric distance. Yeah. And I would like to talk about reliable spanners. So yes, these are somewhat similar to fault-tolerant spanners, but I guess much more powerful. So a mu reliable t-spanner is the following creature. So you construct your spanner, and then there is some attack B. So yeah, so you can think, for example, something like there's a pandemic, and a lot of your site in the networks are closed down, and you cannot use them anymore. But you would like the rest of the network to remain functional. Yeah, but it might be huge. For example, in fault-tolerant spanners that I guess a lot of people are familiar, you need to specify this fault parameter in advance. And then, like for example, if you want to cope with f faults, then usually your spanner will be somewhat polynomially dependent on this f. While here, I allow you to kill even 90% of the network. And I want still that what remains will be functional. And the slack here is the following. So this reliability parameter mu. Yeah? And the guarantee is that given such an attack B, there is some superset B plus, which is slightly larger than B, by this 1 plus mu times the size of B. This contains B, obviously. So in addition, you have this mu B sites. And the guarantee is that for every 2 points, which are not in this superset B plus, the distance between them preserved in the spanner up to a t factor. Yeah, so for example, if your mu parameter is 1 over 100, and you killed 90% of the network, then yeah, I kill another 1% into B plus, and the remaining 9% will remain well connected. So this is the structure. And Buchin, Har-Peled, and Ola, they proved a meta-theorem stating that if you have this tau epsilon LSO, then you can construct a mu reliable 1 plus epsilon spanner with number of edges being n times poly tau over mu. Yeah, and if you plug in the result by Chai and Lau, then you get an Euclidean mu reliable spanner with stretch 1 plus epsilon, a number of edges being like linear in n times epsilon to the minus d times some polynomial dependence in this reliability parameter. So just to note, without any reliability, Euclidean spanners have the stretch of n, the number of edges being n times epsilon to the minus d. So you really don't lose anything significant here. And you get this reliability guarantee. And I will not go over the construction, but yeah. It's actually not completely trivial, but you can imagine, I mean, this reliability, reliable spanners, I mean, this looks from first glance that this will be very hard to get. And indeed, before LSOs, the only construction that had been known were for like B plus being of size beta square and the like. And now we just construct a reliable spanner for each path, which you essentially just put an expander on a path. This will be your reliable spanner. And then you do it for every path in your LSO, and the union of everything will be your reliable spanner. Yeah, so essentially you get this. And now you can plug our LSO for doubling metrics. You'll get a similar trade-off. So this is actually exactly the same as we have for general doubling metrics up to this log n factor here. And yeah. And now we have these two meta-theorems for reliable spanners from triangle LSO and left-sided LSO. And again, you will get this, yeah, all this bunch of reliable spanners. So let me just note for planar graphs. So, so two notes. So first of all, the spanner is not planar. Yeah. And the second thing, so you have this factor 2 plus epsilon here. So you can, it's planar. Usually we like to get 1 plus epsilon, but actually you cannot. So consider the star graph. The star graph is planar, obviously, but the metric on the ellipse of the star graph is uniform metric. So to get any type of reliability parameter on the star, if you want to get stretch smaller than 2, you must add all possible edges. So to get anything below 2, you must have n square edges, and yeah, and we get here like essentially linear size with 2 plus epsilon factor. Okay, so this is all what I wanted to tell you about reliable spanners. The next application I want to discuss is to nearest neighbor search. So nearest neighbor search was, like I guess in our community, a big success story in the last 3 decades. So we got excellent nearest neighbor search for Euclidean spaces, LP spaces, and then even for some eddy distance, Frechet distance, and a lot of very weird different metric spaces. But not for all. So we don't know anything about general metrics, and even say about planar graphs, we know very little. So here was we know about planar graphs. Think of it as a case study. So this is the only paper that we're studying nearest neighbor search in planar graphs. This is the framework. You have your huge planar graph with big n nodes, and I give you a subset P of n terminals, and now you should construct some data structure. Such that given, so these red points are P, and now we're constructing some data structure such that given some query point Q, you should return some 1 plus epsilon approximate nearest neighbor. This is the nearest neighbor among this set P. Yeah, this is the goal. And here's what we know. So this is resolved by Abraham, Chechik, Rutgers, and Wider. So if you assume 2 things, so first of all, you're giving me an access to an exact distance oracle. This means that given this query Q, I can query the exact distance between Q to any point in P. And in addition, you assume that the maximum degree is delta. Then they constructed a nearest neighbor search of size. So you have here linear times essentially the max degree. And the query time is logarithmic times this, again, maximum degree, times the time of the exact distance oracle. So yeah, so if the distance oracle is very fast and the degree is small, this is nice. But in general, planar graphs does not have small maximum degree. And distance oracle, I mean, we have very good approximate distance oracles, getting like, so essentially, I guess, constant even query time or logarithmic and linear size, but it's 1 plus epsilon. And if you want exact distance oracle, then the best we know, and even this was not trivial, is either polynomial query time or superlinear space. So I mean, why? Yeah, why don't use approximate nearest neighbor? Approximate distance oracle. And what Abraham et al. Showed that these 2 conditions are necessary. So in fact, you must be linear, have linear dependence on the maximum degree, and you must use exact distance oracle. So if you give me instead an approximate distance oracle, they construct some examples when you must query essentially linear number of times until you get any meaningful answer that helps you in your search for nearest neighbor. Yeah, so this looks to be the end of story. Yeah. And then we noticed the following phenomena. So in all this story about the success in nearest neighbor search, all these spaces has in common an implicit representation of distances. What does it mean? That, I mean, in this case, I only give you a name of a vertex. This is like meaningless. It's only a name. What can I do with a name? Well, here I give you a vector in Euclidean space, for example. And the vector is great because the vector, like you have these numbers, and you can sort them, you can cluster them, you can do like many different data manipulations. So this is quite useful. What will happen if, for example, in planar graph, you will give me some like meaningful name, something that I can use. And this is the framework we propose here, which we call label nearest neighbor search. So this is the framework. You have your, again, huge planar graph with n, big n points. And you get to assign to each point some label, which is in a sense the name. So if these points were being in Euclidean space, the name will simply be the vector. But in planar graph, you maybe can do something else, something meaningful that will help you later. And I mean, once you're done and give these real names to each vertex, I will give you your subset P of terminals, and I will give you the labels of these points. And now you need to construct a nearest neighbor data structure, such that given a query, and when the query arrives, it will of course arrive as a label, not just a meaningless name, you should return a 1 plus epsilon nearest neighbor. And so this is the game. And now, using this LSO, we'll be able to construct nearest neighbor search with like the label size is epsilon times log square n. So now this is exactly the number of orderings in the LSO. This, by the way, I'm counting here words, not bits. If you want to count bits, you need to add another log n. And the stretch will be 1 plus epsilon. The space is simply n, the number of terminals, times the size of the labels. So you essentially only store the labels. And the query time is, again, very fast. And I mean, this is the construction. So the label simply will be your placement in each one of the orderings and the name of the orderings you appear in. So this is all I store, all the orderings and all my points and the placement in each one of the orderings. And now, given a query Q, I will simply look in all the orderings that Q belongs to, and I will look on the leftmost point in each ordering. And this point will be a candidate nearest neighbor. And now, in addition to the orderings, I will actually store and approximate distance labeling, which is, again, something super efficient. It's logarithmic size. That's been known for quite a while now. And this, for each one of these candidates, I will simply query the distance between Q to this candidate, and I will return you the closest one. And this will be a 1 plus epsilon approximate nearest neighbor. Yeah, because I mean, there will be some nearest neighbor, and there will be some ordering when Q, my query, and this nearest neighbor are satisfied. And this means that all the points kind of are to the leftmost, not appearing, but all the points here should be farther away from P2 and Q. So actually, there are some additional properties of the orderings, but yeah, but this is more or less the idea. Yeah.
Sorry, just to check, are the labels allowed to depend on the set of terminals P?
No.
No.
Yeah, and actually, yeah, using this framework, we've been also able to construct a nearest neighbor. Yeah, more questions? Yeah, we were able to construct a nearest neighbor search for high-dimensional doubling spaces. So, for example, I mean, for low-dimensional doubling spaces, there have been like a lot of work and quite well understood the nearest neighbor search. But if your, say, doubling dimension is somewhere much smaller than log n, which is a trivial one, but still not constant, then we essentially knew nothing. And now in this framework, we have these results. The query time, again, is kind of dependent on the number of orderings you have. And even for general metrics, which were completely unknown, we get this nearest neighbor search with this usual trade-off of k stretch to n to the 1 over k size, this the big N of the metric space, and the query time is log n. So actually, this is a different technique than LSO. Yeah. Size of label. So this is small n times the size of the label.
How large again?
So this is the label.
Yes.
So you need to multiply small n by the label. I mean, essentially, all these data structures just store the label, and the label contains all the like meaningful information for the nearest neighbor search. Okay. So yeah. So let me wrap up with some conclusions and open questions. So yeah, so there's application of this LSO to many dynamic problems, as nearest neighbor search in Euclidean spaces, closest pair, and the reliable spanners that we discussed, which I guess is the biggest thing that we didn't knew how to do before. There are also applications to more level spanners and labeled nearest neighbor search. We have some other type of spanners that we use them for, like fault tolerant, light spanners, and PET reporting low hop spanners. Some things that we don't yet understand. So first of all is, so actually I didn't go into it, but there's two types of reliable spanners. There's the deterministic one and oblivious. So the one that we had for Euclidean and doubling are deterministic. This means that for every attack B, I have this guarantee on the set B plus, while for all the other spaces, the guarantees were oblivious, which means that the expected size of B plus is at most 1 plus mu times the attack size B. Now, for the deterministic reliable spanners, for general metrics are actually poorly understood. So there's an upper bound of t squared, and the size being n to the 1 plus 1 over t. While the only lower bound that we have is the standard Spanner lower bound, which is t over n to the 1 over plus t. So there's a quadratic gap here. And it would be nice to understand, to know the right answer. And this is one question. Another question is about oblivious reliable spanner for planar graphs. So we get this stretch 2 plus epsilon with this number of edges, and you cannot go below 2, but maybe you can get 2. Yeah. So it's still possible to get exactly 2. It would be nice to see if it can be done. And in addition, again for planar graphs, so this is currently our LSOs. I guess using the new tree covers that were presented here, you can shave one of the logs. Yeah, but we don't have any lower bounds. Yeah, so this is true, but maybe you can even remove that. Yeah, and another space that we don't know much about yet is about LP spaces for P larger than 2. So that's that. Yeah. And the homework is to find more application for this new tool of locality-sensitive orderings. Thank you.
Questions for Arnold? Didn't see you track many applicants. So last one. So it seems in your left-sided definition, it's like it's suddenly changing from the number of orderings to how many orderings are various parts.
Right.
Would it make a difference if you just change it in the original definition?
No. I mean, I don't know how to use it. I don't think it will be useful in the original definition. I mean, in the original definition, you can just concatenate them without losing anything, in a sense. But here, because the guarantee is like to the left, it's important that you cannot just concatenate these orderings.
It is possible that different vertices appear in different sets of orderings. That's the immediate how you concatenate.
Right. Yeah, I mean, it's not immediate. I don't know how to use it. I believe it should not be useful. But, I mean, most of them are tight or almost tight. Up to second order terms. Yeah.
More questions?
So I guess the way like you're constructing these things, or like some of the time you just sort of like take a tree cover and do the tree thing, tree cover. Does the reverse direction hold? Is there some sense in which you might expect LSOs to just be equivalent to tree covers? So if I want to construct a tree cover from an LSO, I mean, it almost looks like it's basically a tree cover, but
Yeah. I don't know about such a connection in the other direction, but yeah, I cannot rule it out. It will be. I mean, it's important to note, by the way, for this. I mean, the LSO, for example, for Euclidean space, it's not that if you concatenate all the distances between x and y, it will be similar to the distance between x and y. The number of points in between could be huge. Right, but yeah.
So I guess whoever can write down the definition of all these three, LSO, the triangle, LSO, and left side. You can write all these definitions down without looking at your notes. I think you are qualified applicants. Okay, that's then Arnold again.